So in this video we're going to be looking at the circumcenter and the incenter a little bit more in depth. So the first thing we're going to do is just one more time go through how to construct each one. So remember, this one we're going to be doing the circumcenter. And remember our little saying for this one is peanut butter crackers. So the P standing for perpendicular, B standing for bisectors. If we draw the perpendicular bisectors, that gives us the circumcenter, peanut butter crackers. Okay, so first thing you want to do is take your protractor and measure the length of this side here, and it's just a little bit shy of 10 centimeters. So I need to find the midpoint, which will be just a little bit shy of 5. Midpoint's the same thing as bisecting. So we measure this side and it is 7.5. So half of 7.5 would be 3 3/4, 3.75. This side, if you measure this side, is also 7.5. So if we bisect that, we see the midpoint here will be at 3.75. Now, perpendicular bisector. Bisector meaning at the midpoint, perpendicular meaning we need to go 90 degrees through that midpoint. So now we use our protractor. Set it up here. We're concerned with 90 degrees, so I'm going to put a mark right there at 90 degrees. Use the straight edge of my protractor. 90 degrees through that midpoint. And we have to do that on all 3 sides of our triangle. Lining it up there so that I'm straight with that side. Here's 90 degrees over here. Make a small mark there. Use the straight edge of our protractor, go 90 degrees through that midpoint. Line up our protractor with this side of the triangle. Here's 90 degrees over here. Degrees. Okay, so where our perpendicular bisectors intersect, this would be our circumcenter. Okay. Alright, and then over here we're going to do our incenter. And remember, to get your incenter, this was the saying was a banana and ice cream. So the A really stands for angle, B stands for bisectors. If you draw your angle bisectors, that will give you the incenter of the triangle. So if I want to bisect the angle, I first need to know how big my angles are. So I'm going to put my protractor here. See that this one's 50 degrees. So if I bisect that, that'll be at 25, which is about right there. Bisect that angle. Measure this top angle here. It's about 82, so half of 82 would be 41. That's right there. Bisect that angle, and then measuring this angle over here is just shy of 50, so we're going to go just a little bit shy of 25. And where our angle bisectors intersect is our incenter. Now, let's remember what the property of each of these are. The incenter is equidistant to the sides of the triangle. The circumcenter is equidistant to the vertices. Okay, so we're going to be diving into and using those properties here. Okay, so why is this useful? We have a little real-life situation here. It says we have 3 snack carts that are selling frozen yogurts at points A, B, and C. These are my snack carts. Each of the 3 carts is the same distance from the distributor, okay, because you don't want your ice cream melting, right? So find the location of the distributor. So here's our ice cream, here's the distributor, and then we've kind of taken this triangle and drawn it over here to where we can understand the mathematics behind it. Understand that these yogurts are carts are at our vertices of the triangle. So if we want to be equidistant to our vertices, then we're looking for the circumcenter. Okay, so notice what they've done here. This right here would be my midpoint. They're showing me a 90-degree line through that midpoint. Midpoint, 90-degree line through that midpoint. Midpoint, 90-degree line through that midpoint. So basically what they've drawn here is our perpendicular bisectors. And so we can visually see that D right here would be our circumcenter. And in the context of the problem, that's where our distributor would need to be located. Okay, another little story problem here. A city wants to place a lamppost so that the lamppost is the same distance from all three of these streets. What should the lamppost be at the circumcenter or at the incenter? If we look at the streets as being the sides of this triangle, then we understand that it needs to be placed at the incenter so that it can be equidistant to the sides of the triangle. That way it can, illuminate each of the streets equally because it's equidistant to each of them. So you can imagine bisecting that angle, bisecting that angle, and bisecting that angle. The lamppost would need to be somewhere about in there, which would be placed at the incenter. So that's how they could use that in a real life situation. Okay, so now we're going to dive into the mathematics of just the incenter a little bit more. So in this figure, please understand what you're looking at. If I'm the incenter, then I have angle bisectors. Okay, so I'm going to use a different color pen. So right here, this purple line, that's an angle bisector. I can see that by my congruency marks. This would be an angle bisector by those congruency marks. And this is an angle bisector. So where all the angle bisectors intersect at N, we would understand that N is my incenter. Now, they're asking us about N to D and N to E. Those are not angle bisectors. Those also are not perpendicular bisectors. These are showing me the property that the incenter is equidistant to the sides. And if I'm going to measure the distance from this point to the side, I have to walk straight on at it perpendicularly to get the actual distance, the most accurate distance. So ND right here is 5x minus 1. And they tell me that NE is 2x plus 11. So we know that those are supposed to be equidistant, which means that they are supposed to be equal. So I'm going to set those equal to each other. And we're just going to solve this equation. Subtracting 2x to both sides. Adding the 1 over. We see that x equals 4. When they ask me to find the length of NF, I have to use that value, come up here and plug it in, and see that the length of NE is actually 19. And actually, if you plug the 4 in over here, you'll also get 19 because they're supposed to be equidistant. Therefore, we know that NF it should be the same, so he would have to be 19 also. Now, then they go on to ask me about NG, which is right here. And they ask me, would NG be equal to 18? Explain. The shortest distance from a point to a line is going to be this perpendicular distance that we've measured in blue. So since this one is a more of a slanted angle here, we would expect this to be longer than our true distance of 19. Okay, so we would say no, it would not be equal to 18, it would be longer because the shortest distance is going to be a straight line, which is the 19 that we just found there. So pause the video here and you go ahead and try number 4. That is 3x plus 8 and 7x plus 2. And then I'll show you the final answer. So you should have gotten x equals 1.5. You need to plug that back into either one of your equations and see that either QM or Q to N is 12.5. Therefore, we understand that from Q to P has to be equidistant, so it should also be 12.5. Incenter is equidistant to the sides. All right. Last one here. Which of these does not belong? You have to be very careful about what segments you're looking at here, okay? So the first one that we're looking at, you need to see that these that I'm highlighting in blue, these are my perpendicular bisectors. And so if I'm drawing perpendicular bisectors, peanut butter crackers, okay, then I must be looking at the circumcenter. If I'm looking at the circumcenter, his property is that he is equidistant to the vertices. So now I'm outlining these in purple, and you'll notice that those have congruence marks showing me that this point P is being equidistant to this vertice, equidistant to that vertice, equidistant to that vertice. So that guy is showing the circumcenter. Looking at this guy here, we see that we have a perpendicular line, and a perpendicular line. Those are my perpendicular bisectors. So I must be looking at the circumcenter again. And again, his property is that he is equidistant to that vertice B, equidistant to vertice C, equidistant to vertice A. So they're showing me that he's equidistant, so I'm looking at the circumcenter. Okay? Even here, the lines that are being congruent are showing from this point P, even though it is outside of the triangle, is being equidistant to this vertice, equidistant to that vertice, and equidistant to that vertice. So that's showing me the circumcenter again. Okay, so it must be this last one that does not fit, does not belong. So what are we looking at here? So the ones that they have marked congruent is this right here. This segment here is congruent to that segment there, and that segment is congruent to that segment there. Notice that is not going to the vertices. That is showing me the distance from P to the side of the triangle. The right angle is there to show you that that's the true distance. The distance to the side is equidistant. That's showing me the property of the incenter. So that's the one that does not belong with all the other ones, because all the other ones were showing you the circumcenter. We'll practice some more of this tomorrow in class.